In the last video, we wrapped up the basics of LVGL and SquareLine Studio. In this one, we will be shifting to the code side, exploring LVGL version 8.4.0 core files. We will cover initialization functions, display driver structure, and basics of widgets like text, images, code part as well. Then, in the next video, we will move on to discuss UI files code that was generated by SquareLine Studio. If you are new here and haven't watched the earlier videos in this series, I highly recommend checking them out first so you will have the right foundation before diving into today's content. Namaste and welcome to Avinashee Tech. Here we break down the world of embedded technology, from understanding controller internals and hardware schematics to writing clean, efficient code for real world applications. If embedded tech excites you, hit subscribe and join the tribe. Okay, let's get into LVGL core files. But before that, let me give you a warning. You are now entering engineering only territory. Buckle up or just nod along and pretend you get it. And hey, hope your brain survives the jargons. We will begin with lvgl.h. This file is the main entry point. It contains LVGL version information and includes all the essential header files that the library relies on. Eventually, this header will also be included in your main application source file. Next, we have lvconf template.h. To use it in our project, we need to copy this file right next to the LVGL directory and rename it to lvconf.h. Once that's done, don't forget to set the preprocessor condition to 1. This tells LVGL that your configuration file is now active. Now, let's go through the key settings. First up, color settings. Here, we set the macro LV color depth to 1 byte per pixel. Hold on, 1 byte? But our SSD1306 is a monochrome display and only stores 1 bit per pixel, right? Here's the catch. LVGL still uses 1 byte per pixel internally, that is 8 bits. That means every pixel in the draw buffer takes up a full byte. To save RAM, we usually go with the partial buffer technique instead of buffering the whole screen. Later, before sending data to the SSD1306 display, these 8-bit values are compressed down into one single bit for each pixel. That job is handled by the setpxcv callback function, which is part of the display driver structure. For example, if LVGL gives us 0 hex FF in 8-bit, that maps to a 1-bit 1. If LVGL gives us 0 hex 00 in 8-bit, that maps to a 1-bit 0. We will see this conversion in action once we build projects in ESP-IDF and CubeIDE. For now, leave the rest of the color settings untouched. Memory. Keep the heap size at the default 48 kilobytes. That's more than enough for our basic project at this stage. Display refresh period. By default, LVGL prepares the draw buffer every 30 milliseconds to refresh the UI. We will leave this as it is. Just note, with the setpxcv callback active, the draw buffer goes through an extra step. Every 8-bit pixel value gets converted into a 1-bit format before the actual calling of the flush callback. This adds a tiny processing overhead. On top of this, we also have the SPI transfer. But at 10 MHz, that latency is basically negligible. Fonts. Under font usage, enable LV font UNSC II8. This font is lightweight and fits perfectly with our SSD1306 limited resolution. Also, set it as the default font. Of course, you can choose other font sizes in the config file or even try out custom fonts. We will explore the code side of that in another video. Examples. Scroll further down and disable LV build examples since we won't be using the built-in demos for this project. And with that, our configuration file is ready to roll. Woohoo! Once we have included lvgl.h header file, the very first function we must call before doing anything else is lvinit. Let's track that down. If you open source, then core, then lvobj.h file, you will find its declaration. Then, hopping over to the corresponding .c file, we can dive into its actual definition. Inside lvinit, here's what actually is happening. Let's see it step by step. Meminit. Remember that dynamic heap of 48 kilobyte we set in the config file? Yes, this is where LVGL actually carves out that memory space. Timer core init. So LVGL sets up a linked list to manage timers, with each node the size of an LV timer structure. This list is fully dynamic. Timers can be added or removed at runtime. By default, 2 timers are already active. Display refresh timer, which ticks every 30 milliseconds, just like we configured earlier. Input device timer takes care of touch, keypad, or mouse input. Later, you can create more timers yourself using the LV timer create API. fsinit. LVGL also preps its file system layer, supporting things like FATFS for SD card access. But we won't be using it in this series, but it's good to know it's there for when you need external assets. Next up in lvinit, we see more core modules being set up. Anim core init. This initializes the animation module. Yet again, a linked list is created, this time to hold animation objects, each node following the LV anim structure. Look closely and you will see a timer created using LV timer create with a 30 millisecond period. Interestingly, this timer is then paused for the time being, waiting until animations are actually used. Display and input lists. Next, LVGL sets up new linked lists, one for display objects, LV disp nodes, and another for input devices. Let's peek into LV disp. At the very start, you will notice it contains a LV disp DRV. This holds the basic display driver info, horizontal and vertical resolution, a pointer to the main draw buffer used by LVGL, function pointers for key callbacks, that is flush CB, pushes the draw buffer to the screen, rounder CB, lets you tweak or extend areas that need refreshing depending on your display specs, set PX CB, which adjusts pixel data formats before writing, and we'll be using it in our SSD1306 project. In short, this display driver is part of the main LV disp structure. And here's a key detail. The linked list managing this display objects is called LV disp LL. Like any linked list, it has a head, a tail, and of course the node size. Next up is the image decoder initialization. Here again, LVGL creates a linked list, this time for image decoders. A new decoder node is inserted and function pointers are set up to handle image loading. In our project though, we will be skipping this step. Instead, we will pre-convert our BMP or bitmap images into C arrays using the LVGL image converter tool. And we have covered this in our previous video. Do check it out. But if you ever want to load raw image files directly from the storage, this decoder module is what makes that possible. After that, comes a quick UTF-8 test. LVGL checks if the environment supports UTF-8 encoding or not. Since both ESP-IDF and STM ID already support it, we are good to go without any extra effort. Then there's an endianness test. LVGL needs to know if the platform stores data in little endian or big endian format. Both ESP32 and STM32 are little endian, so LVGL simply confirms this and moves on. Finally, LVGL sets the flag LV initialized equal to true. That's it. LV init is complete. From this point on, LVGL is fully initialized and ready for us to start creating objects, screens, and widgets through its APIs. Alright, let's quickly take a look at the code section for text and image display. As we discussed earlier in this series, our goal was to create a set of universal core files, something that works across platforms. We first achieved this with the basic SSD1306 library, and later for more advanced pixel manipulation, we moved to LVGL, still with the same goal of universal compatibility. So, the code sections I'll show you here will stay the same whether you are working on ESP32 or STM32 or any other microcontroller that supports LVGL. Here, we have our function GUI task. Inside it, the very first call is LV init, which we have already discussed earlier. Next, we allocate a buffer for LVGL. Now, this is not a full frame buffer, it's a partial buffer equal to just 1/8 of our display height. In other words, that equals to 8 rows or 1 page. That's why the macro disk buff size is set to 128 x 8 pixels. Since size of LV color is currently 1 byte per pixel, the buffer size comes out to be 1024 bytes. And remember, this is just for 8 rows or 1/8 of our display height. Moving on, we define the draw buffer structure object, then call the init function to link our created buffer to buff1. After that comes the display driver structure, the one we talked about earlier. We initialize this driver with default values and later update it with true values. Finally, we attach our draw buffer to the driver, update all the necessary callback function pointers, and then create a display structure object. And with that, our LVGL display pipeline is ready to start rendering. Now I will jump over to lvhaldisp.c in the source/hal folder. When we create a display driver object with all those attributes and callbacks for our SSD1306, we will call lvdisp_drv register with that driver object. Here's what happens inside. A new node is added to the linked list lvdisp_ll. The head pointer now points to this new node, and our disp pointer also links to it. Then, the driver member of disp is assigned to the driver object we passed in as argument. What else? A refresh timer is created for this display, defaulting to 30 milliseconds. A default screen object ACT_SCR is created. Two special layers, that is top layer and sys layer, are also initialized. These ensure certain overlays and system widgets always sit above everything else. You can explore them more in the docs if you are curious. Finally, the screen is marked invalid, so it will be redrawn immediately, and the function wraps up with a timer ready call. That way, by the time lvdisp_drv register finishes, LVGL has a fully linked up display object with refresh, scheduling, layers, and a ready to draw screen. So far, you can probably notice a pattern. LVGL loves linked lists, and for good reason. This makes the system super flexible. It means that things like screens, timers, animations, or even styles can be added or removed dynamically while your UI is running. For timer tick count, we create a periodic timer interrupt with callback LV task, where we use LV function. Note that this timer has a period of 1000 microseconds or 1 millisecond. Before moving on, let's take a quick detour into widget basics, because this will help us understand how LVGL really looks under the hood. So what exactly is a widget? According to the LVGL docs, a widget is basically a building block of the GUI. In code, each widget is represented by an LVOBJ structure pointer, and we will see this in action very soon in our hands-on videos. Widgets can be things like screens, text labels, images, buttons, charts, and so on. Each widget comes with attributes such as style, size, and position. But the most important attribute is the parent. A parent widget is like a container that can hold child widgets, and every child widget must know its parent, except for screen widgets, since a screen itself is the root. Now, as we create and delete widgets dynamically at runtime, RAM consumption naturally changes. This is important to keep in mind when working with constrained microcontrollers. Let's also clear up a key difference between screen and display in LVGL. A display represents the physical display hardware. When you create a display object, you define things like resolution, draw buffer, and driver callback. A screen, on the other hand, is the root of a widget tree. To create a screen widget, we call LVOBJ create and pass null as a parent. When we register a display driver, LVGL automatically creates a default screen and sets it as the active screen. You can then create multiple screens for this same display. For example, a home screen with a button, which navigates to another screen, which might open yet another screen, and so on. But remember, only one screen can be active at a given time for a given display. Also, in LVGL, note the hierarchy rule. A parent can have many children, but a child can have only one parent. That's it. No step parents, no adoption twist,
I'm adopted?
no mystery dad reveal,
I am your father.
strict hierarchy, smoother than any TV drama these days. Back to the code, first we create a screen widget. This is important because this gives us the active screen that we will work with. Next, we create a text widget using our active screen as the parent. To display text, we simply call the setText function and pass in our characters. We can also adjust the alignment using the align attribute. Also, there are so many attributes that you can explore. To control how long a text or image stays on screen, I have written a small helper function called displayHandler. It takes in a duration, and while that time passes, it keeps calling LVTaskHandler, which, by the way, must be triggered periodically so LVGL can refresh the screen. For the demo, I have created two text label objects showing Avinashee tech, displayed for 10 seconds with the task handler running in the background. After the text, we move on to the image widget. Once again, the active screen is the parent. We then call setSRC and pass in our image descriptor. For example, the mustache man image, which comes from the C array we generated earlier with the image converter. I will let this image stay for 10 seconds while LVGL keeps updating. Then I will swap the source to hat woman again for 10 seconds. and then repeat this cycle with skyscraper, tiger, and finally our rose flower. To wrap things up, I add one more text label saying to be continued for our little adventure saga. Alright, that was quite a lot to take in for a single video. And if you have managed to follow along till here, you honestly deserve a salute. In this session, we explored the LVGL source code files, dug into the corners of the configuration file, walked through LV init, explored LVGL widgets, and got to know the display driver setup. In our next video, we will dive into the Square Line Studio generated UI files, understanding their structure, the small tweaks needed, and how they tie back into the universal LVGL core. Until then, keep experimenting, keep learning, and I will see you in the next video. If you found this breakdown helpful, don't forget to hit like and subscribe. It really helps me keep bringing you more deep dives like this. This is Avinashee Tech, signing off.